Welcome to my presentation about parameter extraction from LISA data using trilinear approximations. The intention of this presentation is to answer two questions. First, what are trilinear approximations? And second, how can we use them for the data analysis? Now, before diving into these questions, let us first have a look at the data model. So here we see the model for the Doppler measurements, of which LISA will constantly track 6. Since these Doppler measurements are polluted by noise components which might be even larger than the signal of the gravitational wave, we're normally working with the so-called TDI variables. And those TDI variables are linear combinations of time-shifted Doppler measurements. Now, when it comes to the data analysis, we are interested in extracting those parts of the model that are colored in red here. Those are the parameters of the gravitational wave source. Opposed to that, everything that is colored in blue describes the LISA geometry or the LISA motion, and those are parts that we can recompute. So when we consider this model here, we see that the Doppler measurements as well as the TDI variables depend non-linearly on the gravitational wave parameters. And this is one of the challenges in the data analysis. Now, we suggest that we can approach this data analysis by means of trilinear approximations. But what are those approximations and when can we use them? One fundamental assumption of the trilinear approximation is that the waveform h decouples into a slow and a fast oscillating part. The fast oscillating part is described by a frequency omega 0, which I will refer to as the carrier frequency. Now, this assumption, together with multiple Taylor expansions, allows us to represent the TDI variables by this expression here. And we see that this expression decouples into two main parts. The first, colored in blue, contains only information about the LISA geometry and the LISA motion. And the second part, which is colored in red, contains the contributions of the gravitational wave. Okay, so now before discussing how we can benefit from that trilinear approximation for the data analysis, let's first have a look at the accuracy of this approximation. So for this, we are comparing signals that are computed with the trilinear approximation to signals that are computed with the synthetic LISA implementation. And this comparison is conducted for 3 different carrier frequencies, where for each of those carrier frequencies we have generated 1,000 signals, each having a different polarization and a different sky location. Now, the results, as well as theoretical considerations, show that the relative error in the trilinear approximation increases proportional to the square of the carrier frequency. So in general, we see that the trilinear approximation is a fairly good representation of the LISA data. Now let's return to the data analysis. The key to the data analysis with the trilinear approximations is its special structure. So we have already recognized that the trilinear approximation decouples into contributions of LISA and contributions of the gravitational wave. However, the contribution of the gravitational wave can even further be decomposed. So we can describe it by 3 factors. The first, denoted by F, encodes the waveform. The second, described by E, contains information about Rayleigh rotations and the extrinsic parameters. And the third and last trilinear approximation parameter is k tilde, which directly depends on the direction of propagation. Now, to extract the source parameters from the LISA data, we're going to execute 2 steps. In the first step, we are estimating the trilinear approximation parameters, f, e, and k tilde. And in the next step, we are extracting the actual source parameters from the trilinear approximation parameters. And here we are considering galactic binaries without a frequency derivative, but you could also use the trilinear approximation for signals with a chirp as long as the fast-slow decomposition is valid. Okay, so how can we estimate the trilinear approximation parameters? So this is the part where the special structure of the trilinear approximation comes in. In the first step, we are formulating the least square problem that is associated with the trilinear approximation. And here we recognize that if we fix 2 of the 3 parameters, the problem becomes linear in the 3rd parameter. So a strategy how to recover Fe and K tilde is the so-called alternating least square method. And here we are formulating three updates. In the first step, we are fixing F and K tilde, and we're solving the arising linear problem for E. In the next step, we're fixing F and E, and we are solving the linear problem for K tilde. And in the third and last step, we're fixing K tilde and E, and we are solving the linear problem for F. And those updates are then repeated for a certain number of iterations. We can also mention here that we don't make any constraints on the form of the waveform F. That means if we have 3 TDI variables given, we can at most extract 3 gravitational wave signals. In reality, this is a bit different because only 2 TDI variables will contain information about the gravitational wave. That means we can also only extract 2 gravitational wave signals. Once we have recovered the parameter set Fe and K tilde, we can continue with extracting the source parameters. From K tilde, we can directly compute the position of the gravitational wave source. From the waveform F, we can estimate the frequency omega, for instance, by using the Esprit method. And again here, this could also be extended to estimate the frequency derivative omega dot. From the vector E, we can construct a 2 times 2 matrix B, and we see that B contains information about the extrinsic parameters. We also see that B has a special structure, and due to that structure, we can estimate the extrinsic parameters based on the singular value decomposition of B. So with that, we have derived a 2-staged method to extract the source parameters, and in the next step, we want to apply it to a data set. So to test our procedure, we are applying it to the LDC13 dataset. So that dataset contains 10 non-overlapping verification binaries, and we assigned an index to each of these binaries. And the index increases with the signal frequency. That means signal 10 has the highest frequency, whereas signal 1 has the lowest frequency. To facilitate the analysis, we are first isolating the verification binaries, and we are applying the method to each signal individually. For the isolation of the verification binaries, we are designing a narrow bandpass filter with a bandwidth of 1.5 microhertz. In the next step, we're applying the alternating least square method to the isolated data. It might happen, however, that the method gets stuck in a local minima. And to take care of that, we are restarting the first block multiple times, and each time we are starting from a different initial guess. That also means that we are generating multiple trilinear approximation sets, and we are picking that set which minimizes the error in the L2 norm to extract the source parameters from. Okay, so let's check how good we can estimate the source parameters. So let us first discuss the accuracy in the intrinsic parameters. In our case, that is the signal frequency and the sky location of the source. So in the first plot, we see the absolute error in the frequency estimations plotted over the signal index. And we see that the absolute error ranges in the order of magnitude of 10 to the power of minus 11. In these plots, we see the absolute error in the ecliptic longitude and the ecliptic latitude. And we see that it ranges between 10 to the power of minus 5 and 10 to the power of minus 3. Now, for the extrinsic parameters, we have decided to not show the errors in the parameters themselves, but instead show the relative error in the matrix B. The reason herefore is that for small values of the inclination, it might happen that extracting the extrinsic parameters from B is not unique anymore. So instead of showing the extrinsic parameters, we are showing the error in the unique matrix B. I would also like to mention that on a standard computer, it took us roughly 1 second to estimate the parameters of a single signal. And within that second, we did the bandpass filtering, we restarted the alternating least square methods from multiple different initial guesses, and we extracted the source parameters. Now, let me shortly summarize. In the first step, we have seen that the LISA data can be fairly well represented by trilinear approximations. We have also seen that these approximations have a special structure that allows us to use linear algebra techniques for the data analysis. One such technique is, for instance, the alternating least square method. And based on this alternating least square method, we have designed a two-stage procedure for the data analysis, and we have applied it to the LDC 1.3 data challenge. Now, there are multiple next steps that we could take. We could, for instance, include the frequency derivative, or we could constrain the waveform f so that it takes a special structure. And this would, for instance, be helpful if the data set contains overlapping signals or if the data set is polluted by noise. So with that, I want to thank you for your attention. And if you have any questions or comments or ideas, please feel free to contact us. Thank you.